All right, hello. My name is Anthony Ritz, and I am an instructor for Veritas Prep. And I am happy to be with you guys here today on behalf of Veritas Prep and working with GMAT Club. And I'm excited to talk to you a little bit about math today. So, one of my personal favorite areas on the GMAT is number theory. You see it under a lot of different names: factors, multiples, and divisibility, divisibility and factors, primes, etc. It should be roughly an hour. I'm aiming for an hour session, Gaurav. Sometimes I get a little carried away and we might run a few minutes longer than that. But I'm hoping that we'll have this done shortly after 2 p.m. Eastern. We'll see. I've got a lot of great questions to do and I hope not to have to skip any of them. If possible, I will also try to make these slides available. We'll have to see if GMAT Club has a way to post these up for you guys to download if you want, perhaps in the notes of this session or something. I don't know. I'll have to talk to GMAT Club about that. And certainly the video will be available later for you to go back and watch if for any reason you're not able to hang around. But yes, one of my favorite areas is number theory. Whatever you call it, yes, the whole lesson is dedicated to number theory. Each of these presentations is a little one-shot, single-topic discussion. So yeah, so if number theory is not your bag, feel free to come back in a couple weeks. I'll be talking about something else. We got some other Veritas instructors doing other presentations and many other GMAT Club instructors as well. Okay, thank you very much, GMAT Club. I'm glad we'll have the slides in there. So yes, this is about number theory, which again, factors, multiples in the number line, divisibility and factors, call it what you like, but whatever you call it, number theory is the study of non-negative integers. Okay? Believe it or not, there are people out there who spend their entire professional lives simply thinking about 0, 1, 2, 3, 4, 5, etc. Okay? And that's all they do. If you ask them about negative numbers, they're not interested. If you ask them about pi, they say, ooh, sounds delicious, you know? They don't say, oh, you mean 3.14 whatever, etc. And the thing about number theorists is that number theorists look at these numbers just a little differently from the rest of us. And so I think that the mistake a lot of people make here is that they think of this as another one of those areas where you can memorize a lot of formulas and a lot of sort of rules that you just kind of memorize without necessarily understanding, and you can get there that way, but you can't. Because ultimately, if you want to be successful at the highest levels here, it's not really about a process or a formula, it's really about a whole way of thinking. So in this next hour, what I encourage you to do is to try to shift your thinking and to try to learn to think about numbers the way that these guys do. Because it turns out that the way that number theorists think about numbers is very powerful. And it enables us to solve a lot of problems that we wouldn't otherwise be able to solve. So, how do number theorists think about numbers? Well, number theorists see numbers as built out of their most fundamental constituent parts. And when number theorists build their numbers, number theorists do that by multiplication. Okay? So one of the fundamental principles of number theory is that number theorists multiply. I'm always surprised there aren't more of them. Because they multiply? Get it? Nothing? Nobody. Okay, whatever, you guys are no fun. All right, so anyway, that's the kind of high quality humor you will see if you take a class with me. Anyway, number theorists multiply, and when you build numbers out of multiplication, you see that numbers are essentially bags of prime factors. Number theorists see every number as just a collection of primes multiplied together. And it turns out that trying to figure out what's in the bag is a much better way to think about these problems. So I'm going to actually throw us in with an example and give you a really hard question. And by the way, I have this thing for 700 level questions, and I was told that you guys are pretty high level. Actually, I've hung out in the forums a little and seen it. So I didn't pull any punches here. These are pretty much all 700 level questions. Let's see how you do with this one. What I'm going to do is I'm going to run my little timer for 2 minutes on my phone. I guess I don't have a way to give you a timer, but you can mark off 2 minutes for yourself. About 2 minutes, I'm going to walk back on screen. And since my polling function broke, what happens is after those 2 minutes, I would like you to shout out your answer in the chat. Not until then. Don't shout anything in the chat until I walk back on screen. But in 2 minutes, you are free to shout out your choice. Okay? Go ahead and try this problem. Guys, after 2 minutes, don't post anything until then, please. Again, please do not post your answer until 2 minutes have elapsed. I will walk back on screen. Until then, do not post your answer. All right, I know you've all been chomping at the bit, so let's hear it. What you got? What did you guys get for this question? Shout them out. Couple B's, an A, some more B's. Also, you guys don't need to call me sir, by the way. You can call me Anthony or hey you or whatever. It makes me feel old to be a sir. I don't need that. A couple of more B's, a 36, a 48. Not sure. Okay. The consensus seems to be B. And that's good, because B is in fact the right answer here. So let's talk about how we get there for everyone else who wasn't able to. And by the way, this is closely based off an official Veritas question that is a 700 on GMAT Club, and only about half of people get it right. So hey, you guys are already doing better than the average bear there, and good for you. So the key to thinking about this question, first and foremost, is that any number theorist is not going to look at this and think that their job, oh, that's sweet of you, Gaurav, I appreciate it. I feel very respected either way just by your being here. I appreciate that you took the time to join me. So anyway, the key to this problem is that no self-respecting number theorist would ever look at this and think they're trying to find 18s. Because the number theorist doesn't even believe in 18. You say, hey man, I need some 18s. Number theorist is like, what? What are you talking about? I'm not familiar with this strange 18 concept you speak of. But if you said, well, no man, I need some 2s and some 3s. Number theorist is like, oh yeah, 2s and 3s, I get it. Okay, no problem. We can find 2s and 3s. But, you know, certainly we don't want to go there and try to find 8 copies of 18 because 18 is just a bag of factors. And we can build 18s out of those fundamental components. So the first thing we should do on this problem and pretty much every other number theory problem that's out there is we should prime factor. And when we do prime factor 18, we get 2 times 3 squared, and it's all to the 8th. So what we need is 2 to the 8th and 3 to the 16. We need 8 copies of 2, and we need 16 copies of 3. But then, if I start looking for how am I going to get those things, the next thing I would say is, well, I don't really care so much about finding the 2s, because I'm going to have plenty of 2s, right? Like, I mean, by the time I get 16 3s, the 2s show up faster than 3s. Every other number has a 2 in it. Only every third number has a 3. So by the time I have 16 3s, how many 2s do I have? I don't know, man, a lot, like a ton, like a whole crap load over there, way more than I need, plenty. So I'm not even going to worry about the 2s, because by the time I got 16 3s, I'm going to be all set, okay? So what I'm really looking for then, what I'm really trying to find, is how far we need to go to get 16 3s. Now from there it would be very easy to say, okay, I need 16 3s, no problem. 3 times 16 is 48, and 48 definitely has, you know, 16 3s in 48 factorial, because there's 3 times 1, 3 times 2, 3 times 3, 3 times 4, all the way up to 3 times 16. There's 16 multiples of 3 in 48 factorial. And that's true. But, and this is important, having 16 multiples of 3 doesn't mean we have 16 factors of 3. In fact, we will have more than 16 factors of 3, a lot more, because a lot of those numbers 3 times 3, for instance, 3 times 2, which is 18, 3 times 3 times 3, which is 27, a lot of those numbers will have extra 3's. A lot of those numbers that are only one multiple of 3 contain multiple factors of 3. And when you realize that, then I hope you realize that 48 goes way too far. It's a fun trap answer for the people who didn't think about this in the right way, but it's certainly not what we should be picking, and I hope that it's clear why that's the case. And by the way, if at any point you're not clear on anything I'm saying, I've got a lot of fun problems I want to do, and there's a little bit of a chat lag here, so I'm just going to keep going. But if you make a comment, if you have a question, toss it in there, and I will absolutely take the time, and I will stop, and I will respond to it, okay? So I hope you're clear on everything so far, but if you're not, just let me know, and we'll work it out, all right? That's important to me. I want to make sure you all understand. But now that I know that 48 is too far, that's actually good. I've only got 2 choices left because there's 48, couple things bigger than 48. Those are ridiculous. I've definitely got enough by 48, but I really only need to go back and I need to look at the other 2 answers, 33 and 36, because the right answer must be way less than 48. So maybe I'll just try one of them. I'll try 33. There's only 2 answers left. Can't be that hard. Let's just count the 3's in 33 factorial. Now, if I do this, I can say, well, clearly there's at least 11 3's. Because 3 times 1 through 3 times 11. But now the next thing to notice is I get extra 3's. That's why 48 wasn't the answer, because of those extra 3's. And in 33 factorial, every time I hit a 3 squared, which is a 9, I get an extra 3. I get an extra 3 from 9. I get an extra 3 from 18. I get an extra 3 from 27. That's 3 more 3's on top of the 11 I already had. That's 14 3's I've got right now. But wait, because there's even more than that. Because 27 contains an extra 3. 27 is 3 cubed, and it has a third 3 that I hadn't counted yet. So actually, when I put it all together, I have 15 3's. There we go, 15 3's. Unfortunately, I needed 16 3's. I need at least one more 3. Well, I'm not getting it from 34 factorial because the 34 doesn't provide any 3's. I'm not getting it from the 35, but I am getting it from the 36. In fact, 36 gives me 2 of them, and that's fine. I can have an extra 3. I just can't come up short. So 36 gives me enough 3's, and therefore 36 is the answer. 36 factorial will contain at least 16 3's, and it will contain, obviously, at least 8 2's, and it's the first number that will actually give me everything I need. So what do you guys think of that? Does that approach make sense for this problem? Do you see how we got our 16 3's for the first time from 36? Drew asks, why do we do 11 plus 3 plus 1 equals 15? Because what I'm doing here is I'm counting the factors of 3. And right here, I see 11 of them, okay? I see 3 times 1, 3 times 2, 3 times 3, etc. I see 11 factors of 3 in those numbers, except then I look back and I say, wait a minute, but there was a number in here that was 3 squared. And that 3 squared gave me an extra 3. And there was a number in here that was 2 times 3 squared. And that number also gave me an extra factor of 3. And then I had 3 times 3 squared, and that number also gave me an extra factor of 3, and that's 3 more 3's. But then wait a minute, that number gave me even another extra factor of 3, right? Because that number had 3 3's in it. So if I'm looking at my extra 3's, I've got 1 extra 3, 2 extra 3's, 3 extra 3's, 4 extra 3's on top of the 11 that I started with, and that's why there end up being 15. Does that clear it up, Drew? All got it? So the key to this was breaking it down, seeing prime factors, and trying to figure out how to grab the pieces that I need, rather than trying to grab the whole entire number 18 or something like that. Now let's turn it around and try essentially the same idea, but backwards. See if we can figure out what you won't have. Now I'm going to have us do another 2 minutes here. Again, please do not shout out your answers until I walk back on screen, but please do take 2 minutes and try and figure out what you would pick on this. And when I walk back, you can yell it out. 2 minutes, and please go ahead. Oh wait, sorry, I'm on mute. Okay, let me try that again. That was a little over 2 minutes, because I was muted, and you are now free to shout out your answers. What'd you get? Only one person got an answer? After all that time? I've got a C, a couple D's, an E, D is C. This problem, by the way, is not just 700 level. This problem is rated 95th percentile hard on GMAT clubs. So this problem's a pretty stone cold killer. Curious what other answers we've got here. I've got a few C's, a few D's, a couple E's, and I gather that Jonathan's not alone in saying no idea given the sheer lack of answers and comparing that to the number of people who are actually hanging out and watching us. I'm saying like only a quarter of you have actually said anything here, which is a bummer. I'd love to get more participation. But let me go through this, okay? Now let me start by just kind of going the obvious direction. Yeah, no, I think it's a lot of people. Look, don't be shy about letting me know what you think, even taking your best guess at this. I know it's awkward to be kind of put on the spot, but it's helpful for me to know where people's heads are at. And there's ultimately no judgment here. My philosophy is very simple. I don't care about this question. It's strange that I'm teaching it, but I don't actually care about this question at all. Because, see, this question is not going to be on your test. This question doesn't matter to your score. The only question that matters to your score is the next question. So the only question that matters to me is that next question. And the only thing that matters right now is whether you're learning something that's going to help you get the next one right. So if you give me a wrong answer, but you learn from it, that's a victory for me. I'm thrilled, okay? And I'm not going to judge you for that, because if I think you're getting the next question right, then that's everything that I care about, okay? So let's be a little disingenuous here, if I may. 51, duh, right? I mean, if I'm looking at the numbers from 1 to 50 and I'm looking at the product of them, I mean, 51 is clearly not in there, right? 51 is not among the product from 1 to 50. Do you all agree that 51 is simply not in that product? Yes or no? Is 51 in that product? Yes, it is. Ah. Actually, yes. And this, there we go. That's what I wanted to hear. This is thinking like a number theorist. This is such a great question to ask to sort of cleanly divide people into two boxes. The people who think like number theorists and the people who don't. Okay? Because any person who's not a number theorist looks at the stuff from 1 to 50, and if you ask them, is 51 in there? They look at you funny and they go, no. Duh. Are you dumb? Have you never counted to 50 before? 51's not in there. Are you crazy? But if you ask any number theorist the same question, every number theorist, any self-respecting number theorist doesn't even believe in 50. Because all they see is bags of factors. And again, this is the point. You have to think about bags of factors. You don't see 51. All you actually see is a 3 and a 17. And if you ask me, are a 3 and a 17 among the numbers from 1 to 50? Duh. Obviously, right? Yes, there's a 3 among the numbers from 1 to 50, right? Literally 3 is in that list. And there's a 17. Literally 17 is in that list. Plus, there's a lot more 3s and a lot more 17s. 6 has a 3, 9 has a 3, 9 has another 3, 12 has a 3, and on and on and on. Oh, it's okay, Shirzad. You don't have to retract your message. 17 also. 17's in there, so is 34, which contains a 17. There's lots of 3s and even a couple of 17s. So yes, every number theorist looks at this and goes, well, of course, 51 is in there. But, it's okay if you didn't. It's just, that means that you need to think differently, right? I'm not saying you're dumb if you didn't see it. I'm saying that it's obvious from the right perspective. And the point is about getting the right perspective. Okay? So 51 is in the list, and it's clear, I think, if you think of 51 in the right way. What about 2, Iceman? 2 is certainly in there, but of course, the fact is, I'm trying not to get a factor, right? Like 51's not in there, this is a problem. 51's in there, and this is a problem for me. The fact that it's in there means 51 is wrong, okay? So there's a bunch of people in here who I think took the 51 and used it because they took 1 and 3 and 17 and 51 and added them up and got 62. Several of you told me you picked 62, or whatever that is. I don't know, 72, I guess. I don't know. I can't math. I'm the wrong person to be doing this, I guess. Anyway, you got 72, should be, and it's wrong. It's super duper wrong because, of course, 51 is not the number you're looking for, right? 2 is a prime number. It asks for not prime, so certainly we don't want 2. Okay, the point is, they ask for a number that is not a factor of 50 factorial. The problem is 51 is a factor of 50 factorial, right? 51 is a factor, so 51 is wrong. Now, I'm not done yet. I haven't told you what the answer actually is, but I've told you something it isn't, and I told you that because, first of all, that's something that a lot of people picked, and I want to make sure you understand why it's not correct. And second of all, understanding why the wrong answer is wrong can be very valuable. It can help us see how we get to the right answer instead. So the problem is that I can build 51. I can make it. You know, I've got a 3, I got a 17, I can throw them in there together, and I can get what I want. But this raises the question, can't I build almost anything? Can't I build, 52 and just, like any number you think of? There's 50 factorial is a huge pile of building blocks, which raises the question, what can't I build? And there's one type of number I can never build. Because you see, for a number theorist, prime numbers are the fundamental building blocks of the number universe. You can't make a prime. There's no building these. So any prime number that's not already in the list of 50 factorial, exactly, Arjun, is, any prime number that's not already in there is something that I won't be able to produce by multiplying all that stuff together. So it encourages me to think, what's the first prime number after 50? What's the first prime number I can't get out of this pile of stuff? Very good, Firdevs. It's 53, and Laktutor and Gaurav and everyone else. Excellent. 53 can't be made. And if they had not said not prime, 53 would be the answer, right? We can't build primes. We can't build 53. But they said not prime. Oops. But if we can't build 53, what else can't we build? In a moment, I'll answer my own question, but I'll just give you one more second. If I can't build 53, do you know what else I can't build? I can't build, there you go. I can't build anything that contains 53. I can't do it. I'm missing a piece. Can you build 53 times 2? Well, I don't have a 53. Well, you got lots of 2s. Yeah, but I don't have a 53. I don't have the ability to put a 53 and a 2 together if I don't have the 53. And that's actually the key. Because if I can't build 106, that is going to be the smallest number I can't build. Because I took the smallest prime after 50, and I multiplied it by the smallest thing I could multiply by that would make it not prime anymore. So there's not going to be anything else I can't build other than some prime numbers. Right? I can build anything that's not prime all the way up to 106. But I can't build 106, and it is the smallest non-prime number that I can say that about. It's the first number I can't build. And yes, Sanjay, you can build lots of things more than 50, all kinds of things more than 50. But you can't make this. You can't do it, because you would need a 53 and you don't have one. And of course, now it's as simple as listing out and tallying up the factors of 106, which are, of course, 1, 2, 53, and 106. Tally those up. 162 is the correct answer to this question. D people, bravo. Good job. Do you guys have any questions about this very challenging number theory problem? You like it? Gaurav likes it. Jonathan likes it. I'm happy to hear it. What do you guys think? And again, I think you don't have to be a genius to do this. You just have to see numbers the right way. If you're thinking, what can I build with this pile of stuff? What can't I build with this pile of stuff? That makes you so much better at this than if you're trying to use some rule and some formula. But we're not done. Okay, I'm glad you liked the first couple questions. I'm going to keep going. It's like magic, but it's just a way of thinking, and it's a way of thinking you can master. Okay, you don't have to be a genius to do anything I just did. All right, at all. Let's continue. This is a fun one. Oh, hang on, I got a question. Let me take the question. You're right, Div, it does say not prime, and 106 isn't prime, right? I mean, if they hadn't said not prime, I would have just said, okay, 53, and I would have just kind of been done with it. You know, 53, haha, there you go. But 106, not prime. 106 contains primes because every number contains primes. But Div, do you agree that 106 is perfectly fine to use here because it's not prime? Agree? What do you say, Div? So anytime we're talking about divisibility, the most important things here was not the factorial. It was the word prime, it was the word factor, it was the phrase positive integer. All of these words, positive integer, prime, factors, these are clues that you should think in this way. There's lots of different types of problems that involve factorial. Some are number theory problems, others are not number theory problems. But problems that talk about primes and factors and positive integers are very, very likely to be number theory problems. So Drew, that's what I would be looking at to tell me what this is. Let's do another, okay? I got so many fun high-level problems here. I just want to keep throwing you in on them, and we'll pick up the pieces afterward. Again, 2 minutes. Again, shout out your answer only after I come back on screen. Please try this question. Brand new question, never before seen. And please do not shout out any answers until I walk back on screen after 2 minutes. Verdebs, you seem really confident. Do you want to tell us what answer you picked? And of course, everyone else is welcome to do so as well at this point. Since you clearly know this is trivially easy, tell me what you got. I'm not muted again, am I? No? Okay, I'm not muted. So I'm getting a lot of E's, getting a handful of B's. Seems like about an even split. I would suggest that if you spent only 5 seconds on this problem, it's likely that you overlooked something here. Thank you so much. I really appreciate the participation. It seems like a big mix of B's and E's, maybe 1 or 2 D's in there. You know why E is wrong? Because they could be 0. If you're thinking number properties here and you say, well, wait, 5y squared is positive, and since they add up to 0, 12x must be negative, you're almost right. But 5y squared doesn't have to be positive. 5y squared could be 0, because y could be 0. And of course, then x could also be 0. And so x doesn't have to be negative. Sorry, this answer is wrong. Incidentally, I could also at this point cross off d, because 0 is a multiple of everything, including 7, right? So it's certainly possible, if x is 0, for it to be a multiple of 7. And of course, there's a lot of other values of x that are multiples of 7 that work as well. Yeah, it didn't say positive integer, right? If it said x is, not positive, I could say, yeah, it's not positive, but no. Okay, so I trapped some of you guys, and I'm sorry, I suckered a few people there, but those answers are wrong. Let's see what we can actually do here. Now, I've got this addition here, and it troubles me a little bit because number theorists don't really add. Remember, they multiply. There is one tool that number theorists have for addition, and I'll show you that tool later. But for now, I'm just going to try and avoid the issue. I'm going to move the 5y squared to the other side. And when I do, I get 12x equals minus 5y squared. And now I don't have to worry about any more addition. At which point, I will also go ahead and prime factor, right? And 12 is 2 squared times 3. So I got 2 squared times 3 times x equals minus 5y squared. Everyone good with this so far? Now, from here, okay, some people are speaking other languages, I'm not sure, but okay. So from here, I can look at this and I can say, well, wait a minute, the left-hand side contains a couple of 2's, right? They're right there. But that means there's a couple of 2's actually in my bag of factors. The two sides are equal. They're the same bag of factors. There must be also 2 2's in the right-hand side. Where are the 2 2's in the right-hand side? Where are my missing 2's that must be over here? They must be in the y, right? Or at least they must be in the y squared, right? Y squared must contain 2 2's, and therefore y must contain a 2, right? Y has to contain a 2, and that's fine. Y squared will contain 2 2's. In a similar way, on the left-hand side, there is a 3, and therefore on the right-hand side, there must be a 3, also in the y. But here's the thing. If y squared contains a 3, then y had to contain a 3. Because you can't make a 3 by squaring something. In number theory land, it's all integers. So we're going to need a 3 in the y. But to put a 3 in the y means not just that y contains a 3, it means that y squared contains 2 3's, right? If the 3 is in y squared, this is only possible if y squared actually contains 3 squared. So there's 2 3's over here on the right-hand side. But now if I go back to the left-hand side, I only see the 1 3. Wait a minute, there must be another 3 on the left. Where is the missing 3 on the left? It's in there, isn't it? Doesn't it have to be in the x? Why do there have to be 2 3's? Because when I put a 3 in the y, I square it, right? The y contains a 3, but that means the y squared contains 2 3's, right? If y is a multiple of 3, y squared is a multiple of 3 squared. Does that make sense, Drew? That means I now know that I have a 3 on the left, but of course I've got a 5 on the right, which means I also have a 5 on the left. Where am I missing 5 and my missing second 3? They're in x. But wait a minute, if x contains a 5 and 3, then I'm done. X is a multiple of 15. That's what B said. The answer is B. It was a little bit of a scavenger hunt. It was basically I'm looking around, I'm trying to find my 3, trying to find my 5s, and I got only one place they can be. And now that I found them, I have the answer to my question. Yes. Exactly. That's exactly what I'm saying, Gaurav, and that's why this is the answer. Yeah, the y, well, Fido, the y squared contains 2 2s and 2 3s. The y must contain 1 2 and 1 3. If I asked you about y, you could say y contains a 2 and a 3, right? But of course, on the right-hand side, it's y squared, and y squared must contain 2 squared and 3 squared. Got it, Fido? Okay, good. Let's continue. I got so many problems. I'm just going to keep doing them. But one thing we did learn here is if you have a perfect square, you can't contain exactly 1 3. You can't contain exactly 1 2. Perfect square must have 2 of each, or 4 of each, or 6 of each. Perfect cube must have 3 of each, or 6 of each, or 9 of each. A perfect nth power must contain each of its prime factors in multiples of n. And that was important for this last problem, and may be important going forward as well. How did we get the 5? See the 5 right here? You see the equal sign right there? If these things are equal and there's a 5 on the right, there's a 5 on the left. Where's the 5 on the left? It's in the x. 5 on the right means 5 on the left because that's how equal signs work. Got it, Dhruv? Okay, onward and upward. I've still got a lot of problems to do. I'm debating whether I want to skip this one in the interest of time, but it's such a good problem. Okay, yeah, we'll do it. You guys mind if I run a little longer than an hour, or are you guys going to kill me if it's an hour and a half? Again, it will be available online for you to watch later, and if you do need to duck out, that's fine. But I'll try and get through all 6 of the problems I've got. Anyway, 2 minutes. Go ahead and try this one. All right, so shout them out. One of you shouted out a little early, but hopefully that didn't bias people too much, for better or worse. What do you guys got? B, A, D, A. Not getting it. Stumped. Okay. Again, these are really hard questions. No. Okay, E, D, A, all over the place. This is okay. These are really, really tricky. Again, I didn't come in here to do a bunch of 600 level stuff and bore half of you guys with the trivialities. I'm in here trying to help you guys get 51 math scores, right? So again, anytime you see phrases like positive integers, words like multiple, words like factor, you ought to think this is a number theory problem. And anytime you think it's a number theory problem, you ought to switch into that mode and start going, bags of prime factors is what I care about. But this is not prime. Let's fix that, shall we? First thing I do, same thing we do every night, Pinky, prime factor, right? 72 is 2 cubed times 3 squared. Now, I am looking to get 3 2's and 2 3's out of my P and out of my Q. But that means that one of those numbers must contain 2 cubed. I don't know which one. I don't know if it's P, I don't know if it's Q. But I hope you will all agree the LCM is obtained by taking the highest power found in either P or Q for each of those primes. And so one of those numbers must contain exactly 2 cubed, right? And the other must contain up to 2 cubed. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Do you agree with that so far? You see what's on the board, you see what I just said. Agree? Agree, disagree? Yeah. Jonathan agrees? Yeah? Okay, good. If you all agree with that, then we can play the same game with the 3's. In the same manner, I can say that one of them must contain exactly 3 squared, and the other must contain up to 3 squared. And again, I don't know which is which, right? Exactly, I don't know which is which, but that's fine. We'll figure it out later. Now here's where we get fun, because I'm going to look at that first statement. You get here, that's great. That's a good start. But what did I just say about prime factors of powers? I said in order for a power to be a number to be a perfect nth power, then all of its prime factors must occur in multiples of n. In order for something to be a perfect square, its prime factorization must contain only even powers. Do you agree with that? In order for something to be a perfect square, its prime factorization must contain only even powers. But look at what I've got. One of my things contains 2 cubed, and I need to get to an even power. Well, that's fine, because the other could contain 2 to the first, and when I combine them, I'd have 2 to the fourth. Or the other could contain 2 to the third, and when I combine them, I'd have 2 to the sixth. Remember, the other one can contain up to 2 cubed. So I have at least 2 different options for what the other number is going to have in it. It could have 2 to the first or 2 cubed. And in a similar manner, I need an even power of 3's. I've already got an even power of 3's, 3 squared, so I could just add nothing to it. I could just put 3 to the 0 in the other number, no 3's at all, and I would still be fine. Or I could throw 2 more 3's in the bag, and that's fine too, because then I'd have 3 to the fourth, and that is still an even power. The problem is, in each of these cases, I have 2 different options, and they're going to produce different values for the greatest common factor. So this is insufficient. Right, exactly. We can't tell because the power could be higher or lower. That's exactly right, Jonathan. Statement 1 is insufficient, and I hope you all agree. All follow? Okay, let's play the exact same game. The exact same game with statement 2. All right? Statement 2 says that my product, PQ, is a perfect fourth power. Oh, the last part. The last part I said, look, I could have either 3 to the 0 or 3 to the 2. I could have either 2 to the 1 or 2 to the 3 in one of my numbers. Doesn't matter whether it's P or Q. Call it Q. Q could have 2 to the 1 times 3 to the 0. It could have 2 to the 3 times 3 to the 2. It could mix and match. It could have 2 to the 3 times 3 to the 0. It could be lots of different things. And those different things will produce different GCFs. And since I can produce different GCFs here, it is insufficient to determine the greatest common factor of P and Q. Got it, Arjun? While I wait for your response, I'm going to move on to the next statement. PQ is a perfect fourth power. And what we know is that means that all of the exponents, now we need 3 in one of the numbers, right? The least common multiple says that one of the numbers must contain 2 cubed. One of the numbers must contain 3 squared. They don't both have to have it. And the greatest common factor will take whatever's the least number of 2's and the least number of 3's, and you don't know what that is. Okay. In order to be a perfect fourth power, you must contain only powers that are multiples of 4. But let's see what I've got. I have 3 2's, right? How am I going to get to 4 2's? Well, the other one must be 2 to the first. It has to be 2 to the first, because I can't make it to 8 2's. Because the other one can't go above 2 to the third. It's not enough. So do you agree that the other must contain exactly 2 to the first? And again, I don't know which is which, but either P or Q contains 2 cubed, either P or Q contains 2 to the first. And again, I have to have 4 3's or 8 3's or 12 3's, and therefore, given that one of these has exactly 3 squared, the other must also contain exactly 3 squared. I can't make it to 3 to the 8th. It's too far. So the other must contain exactly, precisely, 2 to the first, and exactly precisely 3 squared, and exactly precisely nothing else, because anything else would have shown up in the least common multiple. You can't have any 5's, you can't have any 7's. That's it. One of them must contain 2 cubed, the other must contain 2 to the first. You're getting it, Jonathan. That's right, because now I know that my 2 numbers must be 2 cubed times 3 squared, and 2 to the first times 3 squared. I don't know which is which, but I also don't care, because regardless of which is which, the greatest common factor is this times this. 2 to the first times 3 squared equals 18. B is the answer. The second statement alone was sufficient. Again, what do you think? I know I'm going fast. I know these problems are challenging, but I got 2 more I want to get to after this. So I hope you're learning from it. I hope you find it interesting, but I'm happy to answer any questions as well. Awesome. Anyone else? Thoughts? Got it? Good, good, good. Questions are fine if you got them. Any other thoughts, feedback? Make sense? Yes, no? Got it. Great learning. Good logic. Awesome. Biswadeep, that is fantastic. If you applied that logic to this problem, that is really high level. Is there an alternative to solve this? Not off the top of my head, Drew. I think this is how I want to solve it. It's very abstract and it's challenging, but again, the point is that it doesn't just let you use a formula. If all you have is some formula for the greatest common factor or least common multiple, that's great, but it's not going to solve this problem. You have to think. All right? You have to think. If you put any multiple of 15 in place of x, then it will also not equal to 0. Are you referring to the previous question, Abhishek? Yeah, no one said it has to equal 0. We just said it could equal 0 in the last one. Well, Gaurav, I am going to post these slides. I also think that if you just go on GMAT Club and you go to the directory by topic and difficulty and you search the 700 level factors, divisibility and factors questions, there's tons of great things there. Your final option is come take a class with me. I'm teaching Veritas classes all the time. We have tons of fun problems like this. We teach advanced classes every now and then. I did one in December. I'm thinking I'm going to do another one in about April. An advanced class where we just do nothing but 700 level questions like this pretty much the entire time. So if you're looking for that, that would be a great option for you. Okay. Yes, Abhishek, you can certainly get x not to be equal 0 in the previous question, but you could also get it to be 0. And that's why x doesn't have to be negative, because it could be 0. It just doesn't have to be 0. Okay, moving along. So we learned what least common multiple, greatest common factor are, how they work. Now, you know, the interesting thing is people do learn rules for this. And for instance, a lot of people have learned the unique factors trick. You know, how do I count the factors of an integer, you know? Did you guys ever learn that trick? You know, you prime factor it, you add 1 to the exponents, you multiply the exponents, and that tells you how many factors there are? You guys learned that before? If you haven't, that's okay, here it is, but you know, if you have, that's fine too, but even then, the point is still, it's not enough to know the rule, okay? It's great that you know the rule, but you need to know why it works. Okay, combinatorics is a good answer. You need to understand that the reason it works is because you've got one more option than the exponent. And the reason it's so important to understand is what happens when I twist it, right? If you just know the trick and you don't know why it works, how it works, the minute I ask you something even the slightest bit different, you're adrift, you're lost. But if you get it, if you understand why it works, if you understand that what you're saying is my number of choices for each prime factor is 1 more than the exponent, because I could take up to that many or I could take none of them. You know, if I got 3 copies of 7, I could take 1 7, 2 7s, 3 7s, or no 7. If you understand that, then when I throw you a twist, it's nothing. It's just the same as every other problem and you knock it out of the park. So that's what I'm going to do now. I'm going to throw you a twist. And we'll see if you just memorized the rule or if you actually think like a number theorist. 2 minutes, and then you can shout out your answers, not before. Alrighty then. Okay, let's go ahead and throw our answers in. Abhishek, are you still asking about the question from 2 back? Unfortunately, I don't have time to go back to it right now, but... Oh, okay, Abhishek, multiples can be negative, all right? Multiples of 15 include positive multiples of 15 and negative. A multiple of a number is actually the only time that number theorists ever really acknowledge the existence of negatives. So it's actually completely possible that you can put a multiple of 15 in x that is a negative multiple and it will work out just fine even with y squared being positive. I hope that clears it up. Okay. so let's see. People are saying C here. I got a D also. A couple Ds it looks like. A couple Ds. I got a question. Bizwodeep says, in actual exam, can we actually take a quick guess when running short of time, seeing a statement mentions a specific number and the other statement gives a generic one? I'm not quite sure what you're referring to. Oh, square was a bit generic, fourth power is a bit specific. Well, what I would say there, Bizwodeep, is that since every fourth power is a square, the answer could never have just been A. Because if a square was sufficient, then a fourth power would be as well. So certainly you could have eliminated A, and that question could have eliminated D. But I don't think it necessarily, and it's probably not, I guess you could have eliminated C as well. Well, I guess maybe not D. You could certainly eliminate C because they're sort of redundant. It's probably not A, it's probably not D. You're basically guessing Bizwodeep between B and E on that last question. All right? Yeah, that's fine. I think I cleared up Abhishek. I think it was the multiples can be negative issue. All right, so now let me talk about this question. Sorry to kind of push it along, but I have one more I want to do after this, and I'm hitting the hour mark right now with our late start. So I'm hoping to get through this and squeeze one more in. Now, Gaurav said managed to get only 6. And the way you said that, what I'm guessing is that you tried to list them out. You tried to just go through and write them all down. And I suspect you're not alone in that, but it's a terrible idea. Not a good way to do this. It'll take you forever, especially in the 2-minute timer. You'll have a really hard time. And you'll always have that doubt. Did I miss one? Is there another one? Could I have, not caught one of those things that is an even divisor of 1600 but not a multiple of 16? The better way is to prime factor. As always, anytime they're talking about divisors, multiples, again, prime factor. Prime factor this, prime factor that. And when you do, 1600 is 2 to the 6th times 5 squared. All right? And so what I look at, the way I see this is, I have a bag, and in that bag, there's 6 2s, there's 2 5s in there, all right? Now, yes, formulas, whatever. I don't care about the formulas, Sager. I really don't. In fact, I'd prefer that you not, because what I want to see is that you can think about these problems. Because again, that's the only thing that makes me know that every possible twist I can throw isn't going to bother you. So, I see in my bag 6 2s and 2 5s, and I say any factor of 1600 just comes from pulling some stuff out of the bag. Whatever I pull out, it's a factor of 1600. I reach in there, I grab a couple 2s and a 5, got them all together. I call it 20, and I'm like, yeah, hey, guess what? 20 is a factor of 1600, 2 2s and a 5. Maybe I just pulled out 3 2s and no 5s. That's 8. Yep, also a factor, etc. Any way that I reach into this bag of stuff and pull out something, or even if I don't pull out something, if I pull out nothing at all, that's 1. And that is also a factor of 1600. But what does it mean that my divisor needs to be even? I like that, antimony. That's a much better way to think of it. That's exactly what I'm about to explain, precisely. Use the factor count plus 1 formula. I understand what you're saying, Sager, but still, I'm trying to even get away from that formula. I like what antimony said. What does it mean for my number to be even? As a number theorist, you have to have at least 1 2. That's exactly how a number theorist would think of it. To be even means there's a 2 in the bag. Bags of factors, I've got a 2 in there. What does it mean for my number to not be a multiple of 16? What don't I have? I don't have 4 2s. 16 is 2 to the 4th. So I have to have at least 1 2. But I can't have 4 of them. So what antimony said, again, is beautiful. I love it. That's what I want to see. You could have 1 2, or 2 2s, or 3 2s. You have 3 choices for the 2s. You can take 1 of them, or 2 of them, or 3 of them. Got that? 1 2, 2 2s, 3 2s. And then I go looking at the 5s. But I can contain any number of 5s I want. Whether I'm a multiple of 5 has nothing to do with whether I'm even. Whether there's a 5 in the bag has nothing to do with whether I'm a multiple of 16 at all. So could I have a 5? Sure, of course I could have a 5. Could I have 2 5s? No problem. You want all the 5s, you take all the 5s. Could I have no 5s? You hate 5s? That's fine too. Don't forget you could take 0 of them. I mean, not for the 2s because they said even, but in general, you can take 0 of a factor. Explain the 2s again. Since I am even, so if I look at this, I got 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, right? Those would have been my choices. But even says not that, because that's odd, right? Having no 2s makes me odd. But not multiples of 16 says not this, not this, not this. Those are all going to give me at least 2 to the 4th, and I kill them. What's left? These things are all even, but not containing 16. That's why there were 3 choices, Dhruv. Okay? I had 3 choices for the 2s. 2 to the 1st, 2 to the 2nd, 2 to the 3rd. They're all giving me even, but not giving me 16s. And I have 3 choices for the 5s. Any number of 5s I want is fine. The even has nothing to do with it. The 16 has nothing to do with it. You want 1 5 or 2 5s or no 5s, that's fine. So I got 3 choices for 2s. I got 3 choices for 5s. Number theorists multiply, remember. I multiply, not add, and 3 times 3 is 9. There are 9 even factors of 1600. They're not multiples of 16. And the point here is, we didn't just plug some formula. We thought about it. We understood some formula. We know why the formula. And once you have that, there's nothing they can do to stop you. They can't win once you have that depth of understanding. That's what I care about. Do you have any questions? Any thoughts here? Questions, comments? Give me something. What do you say? I want to get to one more problem after this. You like it? Okay, good. I'm glad you like it, Arjun. Anyone else? About half of these are my personal questions. Another couple are Veritas, more generally questions. They're all from Veritas one way or another. But they're all based on official questions, so we're never straying too far from something you could see in the test. Why did I multiply it last? Well, the simplistic answer is because number theorists multiply. It's just what we do. I have one more. Hang in there, Gaurav. Don't leave yet. I got one more. Number theorists multiply. But beyond that, what you could say is it's really combinatorics. I've got 3 choices for the 2s. And I got 3 choices for the 5s. Oh, I actually got the wrong 3 choices there. 2 to the 1, 2 to the 2, 2 to the 3. And if you think of it almost as like a grid, you could say, okay, well, I got a 3 by 3 grid that I could fill in with all of those choices, you know? So I'm multiplying my options. Because if I had 2 to the 1, I could take this or this or this. If I had 2 to the 2, I could take this or this or this. If I had 2 to the 3, I could take this or this or this. Abhishek, does it make a little bit of sense why I'm multiplying here? Anytime you're counting options, this goes into combinatorics, and that's a whole other lesson topic. But within combinatorics, if you're choosing some number of one thing and some number of the other, you always multiply, and that's what we're doing here. One more problem, but I do want to say something about it before I get in there. You know, so far we've talked number theorists multiply over and over. I keep saying that, but you know, we're not really good at adding. Number theorists, we don't do so well when you start putting pluses and minuses in there. The only problem we had that had an addition, I just immediately got rid of it so I wouldn't have to deal with it. There's really only one rule we've got. That's why. Like, number theorists just don't have good tools for this. The only real rule that we have for when we're adding or subtracting within number theory is what we call the universal divisibility rule. And the universal divisibility rule says that if you have a multiple of any number, plus or minus any other multiple of that number, the result will still be a multiple of that number. But if you have a multiple of any number plus a non-multiple, the result will be a non-multiple. For instance, if I take any multiple of 7 in the world, and I add literally any other multiple of 7, the result will still be a multiple of 7. But if I take any multiple of 7, and I add anything in the world that's not a multiple of 7, the result will not be a multiple of 7. And frankly, if you ever get a number theory problem that really genuinely involves addition and you can't make the addition or subtraction go away, you're pretty much going to have to rely on this rule, because it's basically all we've got. So I want to show you one problem that does that, and then we will wrap it up. Again, I'm going to give you 2 minutes, and you can shout out your answers after that. It is a really useful rule. It's just the only one we've got. Go ahead, please. And that's 2 minutes. So I hope our very last question was fun and interesting for you, and I'd love for you to throw your answers in the chat. Throw some answers in there so we can talk about it and get you on your way. I know it's very late where you are, and for some of you, and maybe very early for others. So what do you got? I've got a 19, I got a 13, I got a D, a couple more Ds. Okay. So don't have a lot of answers here. I assume this was pretty hard for a lot of you guys. The answers I'm getting are good, but a lot of people I think are probably in TT's boat and have no idea. So I want to know what's a factor of both of these things, but that means that I'm probably going to need to get rid of the X, because the X is in my way. I don't know what it is, and all of them could be factors of both of them. Trial and error. Wow, that sounds painful. Okay. So I need something that's simultaneously a factor of 2x plus 1 and 4x minus 50. And that's a bit of a trick because I don't know what x is. I'd like the x to go away. Okay? Oh, all the questions were hard. Oh, okay. I was like, how are all the answers factors of both of them? I was like, did I mess this up? Yeah, they were all hard, but that's okay. They're meant to be, Shamik. I just want you to learn. But, you know, again, I know that a lot of the people who hang out in the GMAT Club forums are really looking high level, and I wanted to give them something really challenging to get to the 700 level. We also run a lot of questions and a lot of classes at a whole bunch of different levels that aren't all 700 level all the time. So I hope I haven't scared anyone off from us. Just, you know, make sure you get yourself in the right class. You take an advanced class, you're going to get this kind of stuff. You take a regular class, we'll tone it down a little for you, and we'll start out at maybe a more reasonable level and help you walk before you can run. But a lot of you guys were already looking to run here, so that's what we did. Now, I want to make the x go away, because the x is annoying me. It bugs me. And what I know, not scared, but boost confidence. Okay, great. What I know is that I can combine these any way I want, because any sum or difference of these will still be a multiple of whatever that factor is right now, right? If it's a factor of this and this, then if I add them together, it will still be a factor because of the universal divisibility rule. Whatever is a factor, when you add them together, if it's a factor of both, it's a factor of their combination. But adding them won't make the x's disappear, because this has a 2x and that has a 4x. But what if I multiply this guy by -2? Now that will still be all the same factors as before, right? Putting another thing in the bag, throwing another 2 in there, doesn't change the factors I already had. Whatever factors I had before, I still got, right? So if I made this -4x plus 2, then I could combine these. Oops, sorry, that's a minus sign. Oh, sorry. I knew something was wrong. I'm such an idiot. Okay, I'm sorry. Let me try that again. -4x minus 2 because distribution's a thing, Anthony. Right. Distributive rule. I knew that at some point. And so anyway, I could multiply by -2 and add them up and get -52. Or, maybe I should have multiplied the other one by negative. Whatever. Here, let's see what I did. If I... yeah, I multiplied this one by 2 and I subtracted, right? So if I multiply this by 2, I get 4x plus 2. And if I multiply this by -1, I get -4x. Oh, this should say 50. That's a weird typo. I don't know why that says 20 and not 50. Okay, whatever. Very strange. Well, please forgive my idiocy. I'll correct that before I upload or whatever the slides. Anyway, try this one more time. 4x plus 2 minus 4x plus 50. The point is the x's now cancel, and I get just 52. I can combine these like this because multiplying the first one by 2 and then subtracting them will keep whatever factors I had before because the universal divisibility rule says that's okay. If I had the factors in one of them, I'll still have it when I multiply by 2. If I had it in both of them, then when I subtract them, those factors will remain. So whatever I'm looking for must be a factor of 52, right? Whatever I'm looking for, do you agree that it's got to go into 52? Any integer, yes, Gaurav. Because think about it. If my bag of factors has a certain thing in it, then when I multiply, I'm just throwing some more stuff into the bag. If I have, let's say, a 7 in my bag of factors, I multiply by 5, I just threw a 5 in the bag. There's still the 7, right? It doesn't take anything out when I multiply. So sure, I can multiply by any integer you want, any integer. And that means that I can now combine them and know that I will still have those factors. And this means 52 must contain whatever this mystery factor is. Whatever the mystery factor is, it goes into 52. But if I factor 52, I have the same freaking typo there. I'm sorry. I have this horrible typo that somehow propagated through a couple of my slides. I'm really sorry about that. Obviously, please ignore the stupid part where I wrote the wrong number down. I was tweaking this problem, and I think I tweaked it funny. Anyway, what I'm looking for must go into 52. And that means what I'm looking for must either be a 2, or maybe a 13, or maybe 2 times 13, or 2 squared, but it's got to be some of that stuff, right? Yeah, we needed to eliminate the variable, basically, Sanjay. That's what we're really doing. We're doing elimination. And sure, you can also get -52, right? But that's fine. At 52, -52, they contain the same stuff. They contain 2 2s and a 3, and a 13. And maybe a negative sign, maybe not, don't care. At which point you say, well, 2 and 13 both look like they work. But hang on, because I accidentally introduced the 2. I introduced the 2 when I multiplied by 2 here, but if you look back at the original values, this definitely does not have a 2 in it, right? This original value was odd. I can multiply by 1, Dhruv. Sure, I never said I couldn't multiply by 1. Yeah, I could multiply by 1. It doesn't do anything, but yeah. No, dividing's the problem. You start dividing, you might lose something. I wouldn't divide. I would multiply. I don't know that putting in values is the best way. Great job, Antimony. So anyway, I'm down to 2 and 13, or maybe a combination of them. But then I look back and I go, wait a minute. Now the 2 was fake. I can't get the 2. This number was odd. The 2 came in when I put it in right there, but it wasn't in there to begin with. It must have been 13 I was looking for, and that's the answer. And incidentally, you can get 13 if x is, what were some values of x? If x is 19, 19 works. Because if x is 19, this becomes 39, and this becomes 26 when x is 19. But you're going to have a really, really hard time finding this by hand. Okay, x equals 6 also works, sure, right? X equals 6 is going to give you 13 and minus 26. Sure. So there's some other numbers that can do it. Yeah. So yeah, dividing is multiplying by 1 over an integer, but we're only multiplying by integers here. We're in the land of only integers exist, so I would be careful about dividing. Multiplying, though, pretty cool. So anyway, it is 13, and that was my last question. Sorry again for the typo on the slides. I will get these sent over to the GMAT Club people as soon as I fix the stupid typo. As soon as I get the stupid typo fixed, I'm emailing it to them, and they will post it up in the notes of this YouTube video, I think. Okay? So check back later in the notes. There should be a link to download. If not, I guess they'll let you know another way to do it. Yeah, divide, exactly. Don't divide. You could lose a common factor. That could be a real dangerous thing. All right. So anyway, that's all the time I've got. But the thing I want you to take away from this is that number theory is more than the formulas. It's more than the rules. Number theory is a way of thinking. And I hope that after today you'll think a little differently about it. And you'll see that that way of thinking, when you master it, is powerful and will make your life and your GMAT score a lot better. Now, if you like this presentation, happy to answer any questions you have, and I'll hang around for a minute to do that. But also, I'd love to see you in one of our classes. You know, Veritas runs classes all the time. I personally do as well. And I really enjoy working with you guys, so I hope you'll come back. And yeah, hey, way to go, antimony. Maybe you should teach the next one of these. All right, that's all I got, people. Any questions? Any comments? All right. All right, great, Jacob. I'll see you soon. And thank you for dropping by in between our classes. And everyone else, thank you so much for being here. All right, it was a real pleasure. I will let GMAT Club take the question about the next session. I'll be back in 2 weeks to talk about Diophantine equations, if you're into that sort of thing. And my name was Anthony Ritz, okay? Anthony Ritz, A-N-T-H-O-N-Y. Ritz. That's me. All right, thank you, everyone. Have a good night.